your things there. Come get your test, please. Solis? Right here. What's your last name?
Selena.
Selena George. Okay, there you go.
Thank you.
Sorry about that. Juan is not here. Lauren, no, right? Okay, so as far as the exam was concerned, the grades were actually very interesting. I've been doing this for a long time, and I don't normally get this distribution of grades. Normally what I see is an upside down bell curve. So normally I see, like, you know, here's your A's, here's your F's. I usually see something like this, where I have students that do well. I don't see a lot in the middle, and I see students that don't do well. That's normally what I see. Juan, your test. Here you go. Some of you, the grade is not on there. It might be on the second page. If it's not there, it's online. So this is interesting because look, this is like not even a bell curve at all, right? I mean, standard normal distribution is like this. You should have like a few students that do really well, a few students who don't do well, and then everyone's kind of clumped in the middle. That's called your standard normal distribution. I don't normally see that in math classes. I usually see the upside down bell curve like this. Y'all are just like this is your curve, like that. Okay, which is, I guess, good. I don't know. I mean, it has a little bump in it, but 7 A's, 7 B's, 4 C's, 5 D's, and I would say for like 2 of these C's are 79, so they're almost B's, right? And then like at least one of these D's is almost a C. Let's see. Did I give you back your test yesterday, Oscar? I didn't? Uh-oh. I think I left it in my office. Sorry about that. Caleb, yours is there, right? There's not an extra test floating around, is there? No? Remember, because I showed it to you, right? I think I filed it away with something else. You know your grade, though, yes? We talked about the one problem anyway. Okay. Lauren? Okay. Here you go. All right, so as far as how I graded it, that one problem, number 11, I just threw it out. Okay, I just threw it out. So it didn't hurt you. I don't think anyone got it, so it didn't help. I just kind of like omitted it from the test completely. So I believe, how many questions were there? 12, and then I threw one out, or 13? It was 13, so I threw one out. That's 12 problems. I graded out of 12 problems. Each problem was worth 10 points. So the most number of points you could have got was 120. So if you add up on there, if it says minus 60, then that means you missed 60 points out of 120, so you got a 50 on the test. That makes sense? If you're trying to figure out how I came up with the number, that's how I did it. So our class average on the test, the average on this first exam was a 77.8. So X bar, class average, was 77.8%. And our standard deviation was 16.05. All right, so class average was almost a B. That's, I guess, okay, yeah? I mean, doesn't a C mean average? Like, that's what a C should mean. In college, when you get a C, that means you're average, right? You get average. B is above average, A is exceptional, right? And then the other way is D is below average, F is below average, right? So the class average is a high C, so that's decent, right? Do y'all know the significance of this number? I look at this number almost more than I look at this number. Standard deviation. So I can explain it to you real quickly. Let's say I had 2 students in the class, okay? Just 2 students. And they took this test, and one of them got a 0 and the other one got 100. What would my class average be? 50, right? So the average would be 50. All right, what if I had two students, one of them got a 25, the other one got a 75? What would the average be? 50 as well, right? Or if I had two students and they both got 50s, then the class average would still be 50, right? So do you see that the class average, although it tells you something, it doesn't tell you about how close these scores are to one another, right? So here I have two students that are on the same page, right? They didn't pass, but at least they didn't pass together, right? Here I have one student who gets it, one student who doesn't, right? So when you look at the standard deviation, the bigger this number is, the more spread out the scores are. The smaller it is, the closer, the more compact the scores are. So this would have a standard deviation actually of 0 because they're exactly the same scores. This would have a higher standard deviation. So normally in math classes I think the lowest I've ever seen is like 11, and the highest I've seen is like 23, 24. So this is a pretty good standard deviation. Just means that the class is kind of together. You know, I don't have too much deviation. All right. And even the students who got D's, you know, I think some of you are, you know, on the borderline there, but. And then there are a few students who need to make some adjustments, all right? So there's a famous quote by somebody who says that their definition of insanity, have you heard that before? The definition of insanity?
Process over and over again and expect different results.
Exactly. So a famous scientist named Albert Einstein, right, said that insanity is doing the same thing over and over and expecting that something different is going to happen. Right? So for those of you who struggled on this test, don't do what you've always done. You need to change something. All right? Something has to change on your part if you expect to have a different result. Whether that be study habits, reaching out for help, whatever it is, it has to change, right? In order for you to expect anything different to come, you know, in terms of the test. Any questions before I get this out of here and we start doing more stuff? Questions on the test? I went back and I looked historically at the last few years. I could go back all the way to like 2002 if I wanted to, but I just went and looked at like the last 4 years. I looked at my Cal 2 classes, how they do on the first exam, and then what is the trend after that? Like what does exam 2 look like? What is exam 3 and the final, right? Historically, this is the best test. Okay, for my Cal 2 students, exam 1 is historically where the students get the highest grades. From there, the average for the exams comes down. Now, not dramatically. It's not like we go from a 78 down to a 62 and then down to a 51. You know what I mean? But it does trend down, which means that the exams, the material gets more difficult. All right? So that's why it's so important that you started out strong. All right, I said that to you. Let's start strong here. And I think a lot of you are in good shape to get going here. All right? We good? All right. Let's get going then. We got more to do, right? We are still talking about integration by parts today. All right, so we're on schedule. If you look at our schedule, we are on schedule. And so we're going to talk about more integration by parts. And then next class, we'll move into the next section. Pardon me? 6.1, yes. All right, so 6.1, integration by parts. Let's put the formula up here, just so we have it. If you're doing the integral of u times the derivative of some function, this is ultraviolet minus the integral of v du. That's our formula. It's on your formula sheets, right? That's what we use for integration by parts. Now, before we begin, I want to take care of a couple of little housekeeping things. As you're doing your homework in this chapter 6, as you're doing your homework, you're going to see problems in the book where they have numbers on that integral sign here, right? So let's say they have like e to the x, times x dx. And they'll put some numbers here like 1 and 2 or something like that. You are to ignore that completely, all right? They are doing what is referred to as definite integrals, which we have not talked about. The way we do Cal 2 here is a little bit weird. We don't do definite integrals until we've learned all the techniques of integration first. The textbook does it the other way around. They do definite integrals first, then they do the techniques of integration. So, because of that, you have to ignore those numbers. That's good and bad, I guess. Good because there's a little bit less work for you to do. Bad because when you check your answer in the back of the book, it's going to be a numerical answer. It's not going to be what we're doing in here where we get a function plus c, which means my homework solution videos are going to be very important for you to kind of follow and see if you're getting the right answers, all right? So that's the first thing. Ignore these for now. I will let you know when you can start paying attention to those. In the homework, in the schedule, it says something like ignore something, right? Doesn't it?
Yes.
Yeah, so that's what I'm talking about. Ignore this stuff. Just treat these as indefinite integrals. That's the first thing. All right. The next thing, where's my sheet? I have a lot of things I wanted. I picked some problems that I've never done before that I thought would be fun to go through today. Okay, so that's the first thing. The next thing I want to look at is an integral. This is not integration by parts, okay? This is just an integral that you need to see, all right? So we're going to just do it, and then we're going to need this later today. Okay, it's this integral antiderivative of secant x dx. It looks like a very unassuming integral. Like it doesn't look like that's going to be hard, all right? We're trying to find the antiderivative of secant x. Now, I can tell you right now, you can throw everything you have at this, all right? You can try weird substitutions, you can try integration by parts, you can do all these things. Nothing is going to work, okay? Nothing's going to work. So I need to show you how this is actually done, and then when you see it, you'll be like, well, shit, I would have never thought of that. And I'll agree with you, I would have never thought of that as well. Somebody else just figured this out at some point. They invested enough time and energy into it and figured out this is the most efficient way to do this problem. All right, so do y'all take my word that this is not possible to do with anything we know so far? Do you take my word? Yeah? Yeah? Okay. So here's what we're going to do to get this to work. And you have to appreciate somebody like really suffered through this. They worked on this probably for, years trying to figure out, I don't know if it's that long. No one gets credit for this. So this is what someone did. They decided to multiply this by 1, right? dx, which is that's allowed, right? You can multiply anything by 1. So the 1, though, that they chose was just, yeah. Okay, so here's what they did. They multiplied by something over itself, right? Okay, the thing that they chose was secant x plus tangent x. Secant x plus tangent x. And that's just so unnatural for anyone to ever just like, oh yeah, that's what I'm going to use, right? But I think after you see this worked out, you'll say, you know what? That kind of makes sense now. Maybe. We'll see, right? All right, so let's now just distribute through the top. Okay, let's distribute secant through. So you get secant squared x plus secant x tangent x, right? All over secant x plus tangent x dx. Do you all agree that's what it is? And it doesn't look like it's any better, right? That doesn't look any better. It looks like, why would you make something so nice and clean into something so ugly? Does anyone see it?
You can find it, break it into parts.
How do you mean? 1 plus a number.
Do 1 over secant x plus tangent x, and you move the numerator off to the side.
Move this off to the side. You said 1 plus, no?
I was probably wrong.
No, I mean, we're all trying to look at this and figure it out. You could do like secant squared over this, and then this over this. Is that what you're saying? Yeah, you could do that. That would be a legal move.
Well, we can take the derivative of the two top ones. Yeah.
Take the derivative of those.
I mean, antiderivative, sorry. So split it up and somehow.
If you split it, you would have to do this over the whole thing, then you'd have to do this over the whole thing, right? If you wanted to split it. You couldn't just do antiderivative of this one, then antiderivative of this one. But all of you are trying too hard. It's here, okay? A U substitution, basic substitution. What's U? What? I heard it. The denominator. Secant x plus tangent x. Let U be secant x plus tangent x. Okay? Make that substitution. I'm doing basic U substitution, not this, right? Not this. What's the derivative of this? It's the numerator. Secant square, sorry, I did this backwards order. Hold on. Derivative of secant x is secant x tangent x, right? Plus derivative of tangent x is secant squared x. And isn't that exactly what's in the numerator? That's exactly what's in the numerator. Isn't that nice, right? So all of this up here, right? All of that is du, right? And this on the bottom is u. Isn't it? Everyone see it? What does this new integral become then? 1 over u. That's what the antiderivative will be. 1 over u du, right? That's what this is. And that we know is natural log. So this is natural log of the absolute value of u, right? Let me put it over here. This is the natural log of the absolute value of u plus c. Now what was u? It was that. Yep. So if you look at your formula sheets, this formula is on there. I'm going to show you so you can see it. On your book formulas, where is it? There it is. Formula number, what number is that? Formula number 14. Do y'all see it there? Formula number 14 on your formula sheets for antiderivatives. The antiderivative of secant u du is natural log of the absolute value of secant u plus tangent u. All right? So, yeah, right? Interesting. Okay. So, yeah, you would never be given a problem like that where you have to come up with that one and, like, you know, I expect you to figure something like that out. But you need to know that these formulas are here, right? All right, that's the first problem. You ready to move on? Let's do a little bit more housekeeping before we get to this first major problem for today. If I wanted you to give me the antiderivative of e to the 4x dx, see if you remember what we talked about here. What would the antiderivative of that be? 1/4 e to the 4x plus c, right? So basically what we had here was e to a linear expression, right? So because this is linear, we have to scale out by the 4, so we put 1/4 here, right? And we do the same thing for like cosine and sine. We have that scaling, right? So if we had integral, let's say sine of, how about this? Beta x dx. So I'm telling you that beta here is a constant. This would be, what's the antiderivative of sine? Negative cosine, right? So we would need a negative 1 over beta, then cosine beta x plus some constant, right? Are there questions or no? This is the same thing we did before, except I'm not putting a number here. I'm just putting it's a constant, but it's a variable, right? Same with up here. If I change this one, let's say we change that 4 to let's go with alpha. And I tell you that alpha is a constant. Over here it becomes 1 over alpha, and then this becomes alpha x, right? All right, I wanted to do that because now we're ready to do our first major problem for today, all right? This is a pretty famous problem with integration by parts, all right? Because of what happens during the actual implementation of the formula. So I'd like us to find the antiderivative of e to the alpha x times, did I do sine? Let me do what I did over here because I need this for later. I'm recording, yes. Sine beta x times sine beta x.
Is that one where you get the same integration after you're looping it?
Yes, this is that example. Yep. Hold on. Let me just make sure I did hit. Yeah, I did. All right. Sorry, my beta looks terrible there. All right, so I would like to know what the antiderivative of e to the alpha x times sine beta x dx is, right? So you start thinking about what is it that you know how to do right now, right? Like individually, you could find the antiderivative of that by itself, sure. You could do that one by itself, sure. But we know that that's not the way antiderivatives work, right? Unless that was a plus or a minus. So we have to somehow try and undo this product. And so, if it's not something you can do a basic u substitution on, the only thing we have in our arsenal is that, right? That's it. So we're going to have to make a choice now. We're going to have to pick what we want our u to be and what we want our dv to be, right? Those are the two things we choose. Now thinking ahead, right? Thinking ahead, remember when we last class and then also on the exam, if I gave you something like this, let's just go with sine, let's say 4x dx. If I gave you this, are you to the point where you would know that that should be your u and this should be your dv? Yes? Because if you let that be u in the new integral, it's going to be a what? A 1 dx, right? And then the antiderivative of this will be a cosine. So you can foresee the new integral and you say, yes, that's going to be better, right? Do you see that this is not good though? Here, do y'all see the problem? If you let this be u, does it get any better in the new integral? No, it's still going to be an e to the alpha x, right? If you let this be u, it's going to go from sine to cosine, right? But it still doesn't get better. I mean, sine and cosine are essentially the same when it comes to integration. So do you see nothing is kind of staring at us going, yes, let me be the u, right? Like nothing is telling us what this should be, right? So we're just going to have to pick one. Right? So I'm going to let's go to the e to the alpha x. And then over here, that forces us to let this be the sine beta x dx. All right? That's my choice, and now I'm going to just crank away. All right? What is the derivative of e to the alpha x? Not the antiderivative. What is the derivative? E to the alpha x times alpha, right? So I'm going to put the alpha in front, e to the alpha x. Why is there an alpha in front? Chain rule, right? When you take derivative of e to the anything, it's itself, and then times derivative of what's up here. Derivative of alpha times x is just alpha. We good? Okay, this I need the antiderivative of, right? To get v. That, we just did that one, didn't we? Yeah. Okay, so this is negative 1 over beta cosine beta x. All right, this now becomes ultraviolet, right? Or go into my formula. Ultraviolet, which are the top two multiplied together, right? I'm going to multiply these two together. When I do this multiplication, I always like to pull all constants out to the front. So I'm going to put the negative 1 over beta out front. Then I'm going to do e to the alpha x, and then the cosine, and then the beta x. All right, all that is ultraviolet right there, right? Now I need minus the integral of voodoo. Voodoo is going to be the diagonal here. So minus, I'm going to leave a space in front. This was kind of the standard that I was doing in class, right? I put a minus, then I left a space in case we can pull any constants out of these two. So look at those two right there. Those are the two that are going to be inside the new integral. What are the constants? Alpha and negative 1 over beta, right? Those are both constants. They can come out. So I'm going to pull it out as a negative alpha over beta. So it'll be a plus, right? So I have two negatives. And this is where I wonder, am I doing too much or is this okay? Are y'all all right with this? Everyone follow this? Yes? What's in the integral? What's still here now? E to the alpha x cosine of beta x, right, dx. Okay. Did things get better? No, they didn't get better, did they? This new integral, the only difference between this one and this one is a cosine and a sine, right? But nothing got better. So it looks like right now I'm just going to get stuck in a loop, right? Like I'm just going to get stuck doing this forever. We're going to do integration by parts one more time. Okay? Let's just do it again. So focusing all of my attention right now on this right here. I'm going to just imagine that I'm just working on that. And let me do another integration by parts right here. I'm going to do the same substitution for u, e to the alpha x. And this one, dv, I'm going to make that one the cosine of beta x dx. I wonder if there was ever a meeting when they were building this building, if there was ever a meeting where they're like, you know what? Should we have a seam right in the middle of the fricking board, or should we just have one long board? That would have been a meeting I wish I was at. I'm sorry. I mean, it's so much money, right? Millions of dollars, and you can't get like the most important thing right, you know?
One long board costs 40% more than two boards.
Yeah, but look, they got these desks that have, you know, computers that lift up. You want to try and tell me you can't get a long board on here? You know what I mean? It's just like, just the motors on those, right? By them, just the motors in this row could pay for that board. You know what I mean?
How much do the motors cost?
Well, okay, we're not going to do a price analysis here. I'm just saying, right? You know, I mean, I've seen boards that are this long where it's just an adhesive that goes onto a flat sheet. You know what I mean? You could just do it on the wall itself. You don't have to have a board. Anyway, okay. All right, yes? Okay, what are we doing here? I'm a little bitter. All right, I'm going to finish this out, right? du is alpha e to the alpha x dx. Don't forget the dx. And then the antiderivative here, 1 over beta sine beta, but no negative, right? I'm going to write on that thing just for, right? 1 over beta sine of beta x. All right? So what's in blue here in this blue bracket is going to turn into the ultraviolet minus voodoo off of that table. Let's go write the ultraviolet minus voodoo over here. Okay? Ultraviolet minus voodoo, when I do these two multiplied, I get 1 over beta, then e to the alpha x sine beta x, minus a little space there, integral. So here comes voodoo, which are these two. Any constants come out? Alpha over beta, right? And it's positive. That comes out. So I'm going to keep this negative sign here. Very important that you don't mess that part up. So what is it, alpha over beta? Like that. Still have a minus. What's in the integral? E to the alpha x times sine beta x dx, right? Now we still need to go insert that over there, don't we? But do you see we've gotten this back, and do you see where we are here? This is the original problem. So it really seems like we've done nothing, right? It seems like we've done nothing, but we've accomplished a lot. Watch. I'm going to do this one up here above this. Okay. We're about to have the little happy moment, okay? So here's where we are. The original integral, right? This was the original problem I presented to you. Right? That was the original problem. Said, hey, what's the antiderivative of this? And here's what we have. We have that this is equal to negative 1 over beta e to the alpha x cosine of beta x plus alpha over beta bracket, okay, so that's everything up to here. Now the bracket is going to be all this, right? All this right here. Okay, so 1 over beta e to the alpha x sine beta x minus alpha over beta integral e to the alpha x sine beta x dx, close off my bracket. We good? Let's distribute alpha over beta through this parenthesis. That means it'll distribute to this first term, then it'll distribute in front of this integral. But it will remove the brackets. So we have, I'm going to rewrite this whole thing. Don't worry about it, okay? Your hand might hurt after today because of all the writing we have to do, but it's worth it, right? Maybe. All right, multiply through here. What do we get there when you multiply this to this?
Over beta squared.
Alpha over beta squared. Whoa, that's a weird alpha. Alpha over beta squared, I don't like that. Okay, e to the alpha x sine beta x. Okay, that's the first distribution from here to here. And then here to here, minus alpha squared over beta squared. You could put alpha over beta in parentheses and square it. That would be up to you. And then integral e to the alpha x sine beta x dx. All right, that's where we are, right? And again, you're like, oh, crap, well, I have the original integral over here, right? And it's over here, but wait a minute. That's actually the best thing that could have happened, because we're just going to do some simple algebra now, all right? The thing we're looking for is all of this minus that, right? What I'm going to do is add this entire expression, including the integral. I'm going to add it to both sides of this equation. See, I'm going to add it over there, and I'm going to add it over here. I'm adding alpha squared over beta